Okay, so now after the break, let's talk about reliability because that's actually one of the major problems facing DRAM even now. Actually, from many conversations for both, basically this interesting problem where both academia and industry, we all look at the same problem, and this is the big problem going forward for DRAM, right? So there are many things that can go wrong with DRAM because the RAM cell gets smaller and smaller and smaller. Capacitor loses charges over time. You need to kind of periodically rewrite the data in all the DRAM row. Don't touch the keyboard. Otherwise your data is gone, right? So you can also have faults, which means that because there's only so few electrons in the cell, to measure the correct voltage, it gets harder and harder and harder. And you look at, say, your laptop DRAM, which is a low power DRAM, this problem gets way worse, all right? You can have errors in your DRAM. Some cells can also be permanently damaged, okay? So why does DRAM lose charges over time? Because charge, no, remote. So because charge leaks through the capacitor, right? Similar diagram for the cell, right? Once I have the thing fully pre-charged right here, right here, you will see that it leaks out. So you get the reduction in the charge in the cell capacitor. So what happened is this demand some method to handle this by we need to refill the capacitor again, right? So that it's full again. And that charge leakage lead to the DRAM refresh operation. So what the refresh operation dictates is once in a while, the memory controller need to write the same data over, right, over the same DRAM cell. The timing for this is called TRFI. This determines the refresh frequency interval, as the name suggests, right? This process called DRAM refresh. And during the DRAM refresh, DRAM become busy. You cannot do anything. You have to basically write the data over the same data again. So you cannot service any normal operation. The overhead is also going to get worse and worse and worse as DRAM grow in size because the interval is fixed. You cannot physically change how DRAM operate. That's physics, right? So what can you do? So you can try to refresh in small bursts. Basically, this refresh interval typically is at 64 milliseconds. Every 64 milliseconds, every single piece of your data in DRAM has to be written over again, right? So one thing you can do is you can space out the refresh to ensure that every row is refreshed every 64 milliseconds. So basically, you would do a few rows at a time instead of doing a whole bank at the same time. The benefit here is you have more free time to do something else in the meantime, right? So this is a possibility, but still, it's still a high overhead because you need to refresh the entire DRAM, all right? Again, let's do a quick recap in Thai, okay? ก็คือปัญหาเนี่ยไอตัวอิเล็กตรอนในคาปาซิเตอร์ครับมันหลุดมันเป็นเนเจอร์ของคาปาซิเตอร์คือเขาเรียกว่า charge leakage มันจะคาปาซิเตอร์เราจะสูญเสียอิเล็กตรอนนะครับทุก65มิลลิเซกเนี่ยเราจะต้องทำการ refresh ก็คือการเขียนค่าเดิมทับเข้าไปทุก65มิลลิเซกสำหรับทุกโรสำหรับทั้ง DRAM เพราะงั้นแปลว่าอะไรแปลว่าทั้ง DRAM เนี่ยสมมุติ DRAM เรา2 กิกะไบต์เนี่ยทุก65มิลลิเซกเราต้องเขียนทั้งหมดเลย2 กิกะไบต์รอบหนึ่งถ้า DRAM เรา4 กิกะไบต์ก็ทุก64มิลลิเซกก็เขียนรอบหนึ่งปัญหาคือ RAM เราตอนนี้ขนาดเท่าไหร่ครับ8 กิก16 กิกเพราะฉะนั้นทุก64มิลลิเซกเราต้องเขียนเนี่ยทั้งหมด16 กิกหรือ8 กิกตลอดซึ่งมันเป็นโอเวอร์เฮดที่สูงมากเพราะว่าเวลาเราทำการ refresh เราท เราทำอะไรกับแบงก์อันนั้นไม่ได้เลยสมมติแบงก์ศูนย์ refresh อยู่เงี้ยแบงก์ศูนย์ง่อยถ้าแบงก์หนึ่ง refresh อยู่แบงก์หนึ่งง่อยแล้วปัญหานี้เป็นปัญหาที่ทั้งอินดัสทรีแล้วก็อะคาเดมีเจอตรงกันว่าเป็นอะไรที่จะทำให้คอมพิวเตอร์มีความชิบหายค่อนข้างมากเพราะว่าเมมขนาดของแรมอ่ะมันจะใหญ่ขึ้นเรื่อยๆแต่ว่าไอตัว interval ที่เราต้อง refresh อ่ะด้วยความที่เซลล์มันเล็กลงเรื่อยๆอ่ะการที่จะทำให้มัน refresh ด้วย rate ที่ต่ำกว่า64มิลลิเซกมันยากคือจะทำให้เป็น128มิลลิเซกก็ยากแล้วเพราะว่าตัว capacitor มันเล็กนะครับแล้วมันเล็กลงเรื่อยๆด้วยปัญหาคือมันเล็กลงเรื่อยๆนะครับ so this is a big problem, right? So one thing you can do is to do this in small bursts so that way you can kind of switch to doing and servicing the normal request, right? Sorry about the typo, sorry. Let me fix this real quick. So you can do auto refresh. Basically a group will be refreshed automatically at a time, right? This is kind of like a default thing you get from a modern processor. But again, there are many other ideas that look into the explore option of refresh. One of the earlier work into this, but I mean, to be honest, the same author kind of investigate further, and this technique become not as useful. But one thing you try to do is like, okay, can we look at different portion of DRAM and see, hey, are there portion of DRAM they can refresh at a different interval, right? This paper is proposed in ISCA 2012. The benefit here is you can reduce the overhead of DRAM significantly because you refresh only like basically you only select 64 milliseconds for a bad portion of DRAM and use a higher latency, which is a 256 milliseconds for some other portion of the DRAM, right? So here's the benefit. The downside is basically this is really good. The same author kind of dig deeper and say, if we can really do this, it seems the retention time basically the time where capacitor can hold the charge vary over time, right? So recap in time. ก็คือมันมีไอเดียประมาณ2010 2011 2012เนี่ยเป็นช่วงที่ปัญหาของการทำ DRAM refresh เริ่มถูก expose โดยฝั่ง academia ซึ่งก็คือจริงๆก็ group advisor ผมเองนี่แหละเพื่อนมันก็บอกว่าเฮ้ย refresh เนี่ยน่าจะเป็นปัญหาเพราะว่า RAM มันจะขนาดใหญ่ขึ้นเรื่อยๆแล้วเราก็ดูว่าเราสามารถแก้ retention time ได้ไหม retention time มันถูก define ว่าไอ้64มิลลิเซกนั่นน่ะคือ retention time คือ capacitor มันจะเสียอิเล็กตรอนด้วยเรทประมาณนี้แต่ว่าจริงๆแล้วถ้าเราดูแรมอ่ะเราจะเห็นว่ามันจะมีบางพอร์ชั่นที่แบบว่ามันเป็นเซลล์ที่ห่วยไอเซลล์ที่ห่วยเนี่ยมันต้องใช้64มิลลิเซกแล้วสาเหตุที่เราต้องเซตทั้ง DRAM ที่64มิลลิเซกเพราะว่ามันต้องเมคชัวร์ว่าไอเซลล์ที่ห่วยมันเวิร์กเพราะเราไม่อยากทิ้ง DRAM ทั้งก้อนเนี่ยคือเราต้องเมคชัวร์ถึงแม้จะมีบางพาร์ทที่มันห่วยมันต้องเวิร์กเปเปอร์นี้ก็บอกเราทำไมเราไม่โปรไฟล์แล้วบอกว่าไอ้พาร์ทที่มันดีอ่ะมันสามารถเก็บอิเล็กตรอนได้ค่อนข้างนานเนี่ยก็ refresh ด้วยเรทที่ต่ำกว่าเช่น256มิลลิเซกแล้วก็ทำการโปรไฟล์ก่อนที่เราจะขายแรมก็โปรไฟล์แล้วจะได้รู้ว่าตรงไหนต้อง refresh ที่64ตรงไหนต้อง refresh ที่128ตรงไหนต้อง refresh ที่256ซึ่ง benefit ค่อนข้างสูงมันลด overhead ได้ค่อนข้างเยอะแต่ว่าพอเพื่อนผมมันดิก deeper แล้วพยายามดูว่าเฮ้ยมันทำได้จริงแค่ไหนพอเราเปลี่ยน temperature แล้วก็ทำให้ DRAM มันมีอายุมากขึ้นเนี่ยคือพยายาม age มันอะเราจะเห็นว่าไอตัว retention time มันมีการเปลี่ยนแปลงเพราะฉะนั้นการโปรไฟล์เนี่ยมันยังไม่สามารถ work ได้ right so this basically means okay this technique is still not effective yet so what else can we do there are many more papers into this area about retention time right so if you want to dive deeper into this area, it's one of the more active area. There have been multiple papers, but still, it's still quite a problem because the dilemma is you want to make DRAM smaller and smaller and smaller, but at the same time more and more reliable, which kind of conflict with each other, right? So we just talk to memory cell reliability. There are many things that affect that. There can be things like temperature, age, number of times you write into the DRAM, or even things like random gamma particles hitting your electron and excite the electron and move it out of the capacitor, right? There are papers that basically highlight that these can happen, right? All these factors can cause bit flips. Basically, your bits change from 1 to 0, 0 to 1. And if you want to look at how bad this problem is, right? You can look at this plot where the y-axis shows the bit error rate. This is the amount of error per, like, per a fraction of normalized to 1. Basically, if you look at, say, 10 to the negative 6, means that I can have the rate of error of 1 bit per 1 million bits, right? So if you look at technology, from 28 down to 25, 20, and smaller. So nowadays, we are actually lower than 10, right? Lower than 10. You can see the bit error rate goes way up because you decrease the cell size. Your capacitor gets smaller and smaller. This increases the error rate, right? The ultra-thin dielectric material gets way more erroneous, so it increases the variance between cell and retention time. And with this can make reading from DRAM really hard. So we can, basically one thing we can do is to use error correction DRAM or ECC DRAM. So most data center, most server would use this. The idea is I would add more data as a way to kind of encrypt the key with error correction code. And the key allow you to detect where are the error and also correct the error, right? So there are multiple ways to correct error. The idea for most of them is to add more bits to detect and correct the error. The primitive approach is handling code. You can kind of like do the single error correction, double error detection. Sometimes we call it SecDet. The modern day approach includes things like ECC DRAM or IECC. These allow you to correct error, and it's also now used all the time in data center DRAM. You can buy ECC DRAM from the market. You can also try to push DRAM toward the limit by saying, hey, overclock DRAM, right? You can make DRAM faster by overclock DRAM or maybe selectively oversupply DRAM, increase the voltage. Because when you increase the voltage, electron move faster. You can also make DRAM consume less power. This is more prominent in the LPDDR DRAM in your laptop, right? So your laptop would have low power DRAM that would use less power, okay? So that's all about DRAM. Any question before we move on to more memory technology? All right, so let's move on. Now, as a typical good researcher, we never stop, right? So we keep inventing and inventing. So if you look at modern day DRAM, there are emerging areas, including things like 2D tile DRAM, which is most of the modern, I guess the past generation of graphic processing unit, the GPUs. And now modern day GPU would use the 3D stack DRAM or high bandwidth memory. Sometimes we also call it HBM. If say you look at some market blurbs from say NVIDIA GPU vendors or like basically or other GPU vendors, they will say, hey, we use HBM. These are 3D stack high bandwidth memory. If you also look at Intel Optane technology, for example, RIP, they die, but they also try to exploit non-volatile memory as the middle tier between DRAM and storage. There are so many types of non-volatile memory, which at this point from our community, we have no idea which one would win. There might be more types as well, right? There's a phase change memory, spin torque memory, there's ferromagnetic memory as well. Regardless of that, let's now focus on the more common ones that are already in the market. The 3D stack DRAM. So basically, what does the technology allow you to do? It allows you to basically put DRAM on top of each other. And you can connect them through this metal wire called the through silicon via, right? So this allows you to pack more DRAM on top of each other and tile them close to the CPU. On top of that, the base layer can also implement a simple logic gates. This means you can have mini ALU in there. So the benefit is you get a lot more bandwidth. You're no longer pin limited, right? you have a much higher bandwidth because your connection to the motherboard is 2D. It's a 2D surface area from your DRAM all the way to the CPU, which means you can have more wiring. This means you can have more bandwidths. The bottom layer, as highlighted in this plot, or in this figure, the green stuff, you can put logic there, means that you can have actual compute unit with the memory controller, right? So these allow layers of DRAM chip, which means that you can increase the capacity. Current AMD GPU use HBM now. I think they stopped using Tiling, now use HBM. Sorry about this. The slide's a little bit old. It's like back in actually it's back in like 2019, so it's way older. The layers connect through the TSV or through silicon via. It offers a lot of internal bandwidth and also a lot of external bandwidth. That's why we call this thing the high bandwidth memory. On top of that, you can also put it on the same die as a processor by stacking on top of the CPU, right? That's a possibility. You can also have compute elements within the package, allow for the technique called processing in memory, right? So the 3-stack DRAM, from the abstract point of view, it kind of makes sense. It gives you a lot of bandwidth, it gives you a lot of capacity. But from the architectural point of view, now that you have the logic layer, what else can we do, right? So with the logic layer, you have processing in memory. Think of simple ALUs next to the memory, right? So there has been many works that explore things that you can do with this much higher bandwidth, simple ALU, and allow you to transfer data just to the memory, within the memory. You don't have to transfer data to the cache, so it's much more power efficient. Basically, when I said lower data transfer between the CPU and the memory, this means energy efficiency and performance, right? There's also with PIM, there's no complication with how do you design it, because they also share the same memory as the CPU, right? So there's going to be consistency problem, coherency problem, and even things like enabling virtual memory is not easy, right? So with this, there are a lot of active research into the area. If you guys are interested, definitely let me know, all right? Now, if we move on to the non-volatile memory, the key is we don't use capacitor anymore, which means that if you don't use capacitor, we don't have charge leakage. It means you don't have to refresh, or if you have to refresh, it will be in the factor of days or months or year. And also another benefit is these are denser than DRAM. It means that you're looking at something that has much higher capacity, right? So because you don't have to refresh, it's actually more scalable in terms of adding more capacity. And it has a much lower access latency than your storage unit, which is the SSD. Oh, my bad, this is a typo. Okay, sorry about another set of typo. Didn't saw that earlier. All right, let me fix this. So as I said, it looks like an SSD, but the read latency is roughly the same as DRAM. To be honest, the current technology with an actual device being tested is still higher than DRAM. It's not as good as we thought. And also the write latency, the time it takes to write is really high. Writes to NVM are also bad because most of the time the way you write is you shock the cell. So if you shock something too many times, it dies, right? So similar to SSD, write are destructive. If you write to the same cell too many times, the cell is gone. At the same time, there's so much benefit you get out of the non-volatile memory. So we're still trying to figure out, okay, how do we actually architect this, right? One way we can do this is treat non-volatile memory as a much larger memory pool, because it does allow terabytes of memory. Data is also persistent because you do not have to refresh. Many people are also exploring using NVM, non-volatile memory, as a way to recover from crash. Sometimes we can use this for crash consistency basically means that if the machine crashed, I will have things in non-volatile memory. I can resume right away. There's also no leakage power, so typically these devices are much more power efficient. And most of the time, if you look at, say, Intel's Night Landing, which kind of like, well, again, Intel kind of stopped looking into an NVM for now, right? But people explore how can we use NVM with DRAM or with the 3D DRAM, or how do we use it as a hybrid memory, which means that I use DRAM and NVM together. One of the idea as getting more prominent is, hey, let's use DRAM as the cache for NVM, right? There's been papers since like 2000, late 2000 on these topics. Still explored right now. This is what we call storage class memory. Basically, this allows you to store a lot of things in your DRAM. Okay. Another really interesting non-volatile memory technology is the resistive RAM or RRAM. Sometimes we call this memristor. Sometimes we also call this resistive memory. And it does have really interesting property. Because it stores the resistance, right? It stored the resistance. Oh, sorry. Let me use the pen. Pen. All right. RRAM store resistance. It means that if I want to read into RRAM, I use Ohm's law. V equal IR. Okay. Well, let's keep this in mind for now, right? Cell are basically doing a multiply. If I want to read something, I send the voltage in, I read the current. I mean, it's V equals IR. The bit line sum everything up. What you just got is when you have a 2D array of this, you got a dot product and a sum. A dot product and a sum. A dot product is a multiply. This is the sum. Sum of product is vector slash matrix multiply. So if you see how this is going, you see that, hey, matrix multiply is used for many, many things in neural network machine learning, right? So there are many, many ideas, and kind of start with like some of these earlier work, for example, Isaac, right? It's a paper back in the day that say, hey, let's use RRAM cell to do compute in memory by storing the metrics inside the resistor. You feed in the input vector as a voltage. What you will get is basically the voltage input is a vector. The array is a 2D matrix. You get matrix vector matrix multiplied as a result. So these store your matrix. The input here is your vector. Now you can use this additional like embedded DRAM to like store results. And this is one of the earlier work. There are more follow-up works in this area, including some of my works with the students in China on how do we enable this for like graph application and how do we kind of flexibly use this. So if you're interested in this direction, definitely let me know. All right. But yeah, there are things you can do with this non-volatile memory, but not from the classical non-volatile memory point of view. Okay. That kind of wrap. That's a wrap for the DRAM lecture. All right. So before we leave today, I want to kind of talk a little bit more about memory scaling. I know it's this is quite an old topic now, right? But I kind of still want to mention that because this is basically one of the first topic I ever done as a PhD. So I will talk about one of my first work that I published back in the day in collaboration with many senior people at AMD. So we look into, okay, back in the day, AMD just got ATI technology. They have the GPU now. So they think, hey, we have CPU, we have GPU. Can we integrate them in the same chip, right? I mean, look at now, most modern processor has CPU and GPU together. We have the integrated GPU to share the off-chip memory, which means that both CPU application that you're running on your desktop and the GPU, let's say you're playing games, they share the same DRAM. When they share the same DRAM, they're gonna interfere with each other and kill each other performance. So how bad is the interference at the main memory? So you look at normal CPU scenario, right? You send requests over, and this looks normal. This looks like the typical thing you saw earlier, same thing I have on my slides, right? And again, as you can see, this content for the limited off-chip bandwidth, it can degrade system performance, right? So the scheduler can help mitigate the problem. Here come the GPU. Yay, right? So the GPU, one thing we know about GPU, it have a lot of parallelisms. For those of you who use GPU for machine learning, you would know that you would write a program in the data parallel manner. You access a lot of data at the same time. So this is what happened. Again, they share the same DRAM. Now the GPU flood the entire buffer. And when that happened, many techniques to try to look into, hey, what's my property? And I request from like one of these applications on the CPU. I have no insight into them because they cannot even inject into the buffer. So one simple solution you can do to maybe mitigate this problem is to increase the buffer size, right? I said this is a simple solution in terms of thinking about that. I can increase the buffer size, but these are hard to implement because when you have a lot of buffer, you need more logic to analyze the request, analyze the characteristics, and also enforce whatever policy you want in the scheduler. This really leads you to much more complex scheduler. So the goal of our work is to make sure we still get a really good scheduling decision through our new memory controller, but you want to make it basically scalable, make it not too complex. To do that, we first look back and look at, hey, what's the key function of the controller, right? So these are things that memory controller should do. First of all, it should maximize your buffer hits, right? To do that, in our design, we would basically break the design into multiple stages. The first stage is what we call the batch formation, which has the ability to group requests from the same application into batches. Then you can look at the second stage where it tries to manage which application should get more service. How do I make this fair across all the applications? And the idea is I would decouple all these tasks of the memory controller into different phases, right? Across a much simpler hardware structure, which is a queue. So here's the first stage. I have all the cores, including the GPU, that can inject new requests. Basically, these are access to different roles in DRAM. When I have this, right, I would group the requests that are consecutive and going in the same row together. And if I have a new access to a different row, I group them in a separate bin. We call this a batch. So all the core would keep collecting this group of rows, right? If I have, and also have a threshold that say, hey, if time window expire, I also form a batch. I'll do this for all the core, as you can see here. And then this front, like the front of the queue, once it's formed the batch, it becomes ready to be scheduled. So in this way, the scheduler only have to now look at the front of the queue, in this case, 4 items, right? Now you have all the items in the front of the queue. The second stage, which we call the batch scheduler, the only job is to pick what goes to each bank from the top of each queue here in the first stage, right? So to do this, we use 2 policies. The first policy is shortage of first policy. And if you look into queuing theory and like many of the scheduling work, you will know that shortage of first policy is good for performance. So the way it works is I will pick the batch with the smallest number of requests. In this case, the purple batch from core 4 would be service being sent to the next stage in each bank. Now, I would use the shortage of first and also the round robin policy. The way round robin policy works is it would just rotate which which application get to send the batch over to its own designated bank. So in this case, we'll take turn. We'll do the yellow block, then the red block, even though they're not the smallest one, right? The scheduler would have a probability of P to use shorter job first and 1 minus P to use round robin. And this allow the shorter job first to prioritize the CPU application, and the round robin to give priority to the GPU application because they tend to form a huge batch. And to actually evaluate performance, right, we show on the x-axis here is the different GPU weight. Basically, it means that it's the weight I multiply to the GPU performance. Lower weight means I don't care about the GPU. Higher weight means I'm playing games and I only care about the GPU performance. On the y-axis is the system performance. How much performance do I get out of the system? And I compare this to the best previous scheduler on the red bar here. One of the work is called Atlas. This is really good for CPU. Another work called TCM, this gives a lot more fairness. So as you can see here, it works well when the GPU is kind of considered the same weight as the CPU. Then the FRFCFS, which we already talked about during the lecture, right? This gives a lot of DRAM throughput, so this is really friendly toward the CPU. And what we found is our design SMS is better at all this. Basically, every single scheduler being proposed at that time for every single GPU weight. So basically, we found it outperformed everyone at any of this particular GPU weight. So to quickly summarize, like we kind of look at, hey, when you have CPU, GPU heterogeneous system, you need large request buffers. But the problem is, if I increase the buffer size, it's hard to scale. So our solution is to break them into different stages and perform the scheduler in a way that still keep the raw buffer information and still try to give you fairness between CPU and GPU. This idea is also patented after the internship with this particular US patent number. And again, basically, that's kind of like my first paper. So I'm going to talk about it a little bit because it's relevant to what we talk about today, the memory scheduling. All right. That's kind of the wrap on the lecture portion. Before we leave today, I want to continue on with like a little bit updates on your project. So before that, right, let's do two things. Let me stop the recording because that's the end of the lecture. Okay. And then